Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 33. In this lecture, we'll discuss collisions. This topic is covered in Chapter 9 of our textbook by Survey and Jouet. An important class of problems in physics involves collisions between two objects. Collisions happen all the time at all scales. Right now, as you're viewing this lecture, there are trillions of air molecules that are colliding with each other or with the walls of your room. A tennis ball might collide with the tennis court. An automobile might collide with another automobile, or an asteroid might collide with a planet. So collisions are quite common and they happen on all scales, and it's important for us to study them. In particular, we often want to know what the outcome of a collision will be. So for example, in the collision of a tennis ball and the tennis court, we want to know how the ball will bounce, with what speed and in which direction. In the collision of two cars, for example, we want to know the forces that are involved so we can figure out, for example, the amount of damage that the two cars will sustain. It turns out collision problems can be analyzed quite effectively using momentum and momentum conservation. So our goal for this lecture will be specifically to use the principle of momentum conservation to figure out the outcome of collisions. We will adopt the following model in our collision problems. So we will have two objects, object 1 and object 2. These objects will approach each other before the collision, and then after the collision, they will move off with different velocities, and our goal will be to basically figure out the final velocities. We will assume that the masses are known and fixed. In other words, in all of the collision problems that we'll study, the masses will be known, and the collision will not change those masses. So whatever mass object 1 had before the collision, it will have exactly the same mass after the collision. That's not always the case. In some collisions, masses change. For example, in nuclear collisions, when a neutron collides with the nucleus of a uranium atom, the mass of the nucleus could change, but we will not consider those examples here. Even in the collision of two automobiles, one automobile might lose pieces or components that fall off, and in that sense the mass is changing. We will also ignore that, or we will assume that that's a negligible effect. We will also always consider the collision of only two objects. In theory, you could have three body collisions. In theory, you can have 12 objects simultaneously colliding with one another, but we will keep the discussion limited to the collision of only two objects. Given the initial velocities, our goal will be usually to figure out the final velocities. So we'll say that velocity of object 1 and velocity of object 2 are known before the collision, and our goal will be to use conservation of momentum and other techniques to figure out v1f and v2f. So these are the final velocities of object 1 and object 2. So far in this course, we've learned a lot of useful techniques for analyzing physics problems. For example, we've learned about kinematics and how we can use the kinematic equations to analyze the motion of a projectile. We've learned about energy conservation, and we've used that concept to solve many interesting problems. It's useful to understand why those techniques are inadequate for analyzing collision problems. When it comes to the collision of two objects, there are two internal forces. Just generally speaking, there's the force of object 1 on object 2, and then of course there's the reaction, which is the force of object 2 on object 1. Now, if either one of these two forces is known, then the other one is known as well, because Newton's third law of motion tells us that one of them is basically the negative of the other one. They have the same magnitude, but they point in opposite directions. Unfortunately, knowing these two forces in most cases is not practical, might even be impossible because of the immense complexity of collision problems. If you are talking about the collision of, for example, one atomic nucleus with another atomic nucleus, the type of thing that happens in nuclear reactions, then the force that's involved in that collision is the so-called strong force, which is a very complicated and difficult to model force. If you're talking about the collision of two atoms, the electron cloud around one atom will repel the electron cloud around the other atom, and that's a rather complicated electric force, which might be difficult to model for specific atoms. Even in the collision of two cars, the forces can be quite complicated because the force of car 1 on car 2 will depend critically on how the collision happens, on the shape of the cars, on the shape of the bumpers, what the bumpers are made of, and how the frame of the car reacts to the collision forces. In the case of the collision of an asteroid with planet Earth, there might be multiple extremely complicated forces involved. There is the drag force as the asteroid enters the Earth's atmosphere. If it lands in the ocean, then it will encounter viscous forces as it encounters resistive forces from the water. But if it lands on land, there will be other forces involved. So in general, the forces that are involved in a collision are quite complicated. In general, we don't always know exactly what these forces are. Since these internal forces between object 1 and object 2 are unknown, we cannot calculate the acceleration of the objects. And if we can't calculate the acceleration, we cannot use the kinematic equations. So the kinematic equations are not a useful tool in analyzing collision problems. Since the internal forces are unknown, we also cannot calculate the work they perform. If we cannot calculate the work they perform, we cannot use energy conservation. Remember, energy conservation involves kinetic energy, it involves potential energy, but it also involves the work done by non-conservative forces. So this is one way you can express conservation of energy, where W and C is the work performed by non-conservative forces, and these forces involved in a collision are often non-conservative. If we don't know what those forces are, we cannot calculate W, and if we cannot calculate W, we cannot use this equation to analyze the problem. Momentum conservation, on the other hand, turns out to be an excellent tool for analyzing the collision between two objects, because momentum conservation does not depend on internal forces. These forces that we were talking about, the force of an asteroid on the planet or the force of one car on another car, these are internal forces so long as we view both bodies as one system. So if we view both cars as one system or the asteroid and planet Earth as one system, then these complicated forces become internal. And it turns out that internal forces do not impact momentum conservation. Therefore, we can use the momentum conservation equation as a useful tool to analyze the outcome of a collision. Recall that the principle of momentum conservation talks about external forces. It states that if the sum of the external forces is equal to 0, then momentum is conserved. And you should be wondering why the focus on external forces. What happens to the internal forces? Why are they irrelevant? Remember that internal forces are forces that one piece or one element or one component of the system exert on another piece or element of the system. So if your system is an atom, for example, you might say the nucleus attracts the electrons, and the electrons attract the nucleus. Those are internal forces. If your system is an automobile, then you might say that the engine exerts a force on the drivetrain, and the drivetrain exerts a force on the wheels. These are all internal forces. Why don't these forces matter when it comes to conservation of momentum? Well, the short answer turns out to be Newton's third law of motion. According to Newton's third law of motion, for every force, there is an equal but opposite force. What that means is that if component A of the system is pushing on another component, like component B of the system, then component B must be pushing back on component A. And these two forces simply add up and cancel each other out because they have equal magnitudes and they point in opposite directions. This is the short answer, but there's also a longer answer, a mathematically more sophisticated answer, and it's useful for us to go through this explanation as well. If we want to examine the conservation of momentum, we need to really discuss the derivative of momentum with respect to time. Remember, when we say that the momentum of a system is conserved, what we're really saying is that it does not change in time, and therefore its derivative must be equal to 0. Now, we are interested in the collision of two objects. We will not consider the collisions of more objects than that. So when we talk about the momentum of the system, we have momentum of object 1 plus momentum of object 2. Remember that the derivative of a sum is the sum of the derivatives, which basically means that you can take the derivative operator and distribute it into the parentheses. And so the momentum of the system, its derivative, will be equal to the derivative of momentum of object 1 plus the derivative of momentum of object 2. Now, momentum is mass times velocity, so we can replace P1 with M1 V1, and similarly for P2. We are assuming that the masses do not change in the course of the collision, so M1 is really just a constant, and you can treat it like a constant when you take the derivative. You bring it out of the derivative, and you end up with the derivative of velocity 1. Similarly for the second object. Now recall that acceleration is dv dt. Acceleration is the rate of change in velocity, so we can replace dv1 dt with simply the acceleration of object 1, and dv2 dt will replace that with acceleration of object 2. Now recall that Newton's second law of motion tells us that F equals ma. In other words, acceleration is caused by forces. And so we can replace ma by F. Although we need to be a little more careful. On the left, we have mass of 1, acceleration of 1. So this corresponds to the force on 1. On the right, we have mass of 2 and acceleration of object 2. So these two correspond to the force of force on 2. Now we are assuming that in these collisions the system is isolated, so there are no other forces involved except the force of 1 on 2 and the force of 2 on 1. So M1A1 ends up being force of 2 on 1, and M2A2 ends up being the force of 1 on 2. According to Mr. Newton's third law of motion, these two forces must be equal and opposite. You can tell they must be an action-reaction pair because of the way the indices are written. 2 on 1 has been swapped with 1 on 2. Since these two forces must be equal and opposite, they will add up to give us 0, which proves our original statement, that it doesn't really matter what these internal forces are, they will cancel each other out, and the rate of change in the momentum of the system will be 0, therefore momentum is conserved. So we've spent a fair amount of time discussing the theory behind momentum and momentum conservation. Let's now apply those ideas to an actual collision problem. Two isolated particles with masses 4 kilograms and 1 kilogram collide with initial speeds 3 meters per second and 7 meters per second. After the collision, M1, or object 1, rebounds with a speed of 0.5 meters per second. We basically want to know what happens after the collision. A little more precisely, we want to know the final velocity of object 2. Also, we want to know what happens to the kinetic energy of the system after the collision. Is it conserved or does it change? Notice that this is the typical model of a collision problem for us in this course. Two objects with known masses, 4 kilograms and 1 kilogram. The initial velocities are known. One of the final velocities is given to us, the other one is not. Notice that actually the velocities are not given to us, it's the speeds that are given to us. So we need to be a little more careful as we start doing our calculations. In particular, we need to notice that when we write down v1i, the vector, we should write it as +3, 0, indicating that its x velocity is 3 and its y velocity is 0. And when we talk about velocity of 2, initially we should be very careful to write it as -7, 0. Its y velocity is 0. That's pretty obvious from the picture. What may not be obvious is that the x component of the velocity is in the negative x direction. Notice here the speeds were given to us, and this is the speed of object 2, right? Notice there's no subscript x here. You need to determine from the context of the problem or the picture given that the x component is -7. Why am I talking about the x components? Well, because momentum is a vector, and like all vectors, it has x and y components, and those components can be positive or negative. We need to pay attention to which one they are. Similarly, notice that we're told that object 1 rebounds with a speed of 0.5 meters per second. Again, speed is the magnitude of the velocity vector. It's always given to you as a positive number, but we're interested in the components. So when we write v1f as a vector, we should write it as -0.5, 0, indicating the minus sign, indicating that it's moving in the negative x direction. So equipped with this information and the masses, can we figure out what object 2 is doing after the collision? So to figure out what the second object is doing, we will use the principle of momentum conservation. The problem explicitly stated that two isolated particles are colliding. That immediately tells me that the sum of the external forces must be 0, and therefore I can set the initial momentum of the system to the final momentum of the system. The motion is happening in the x direction. There's really no point in discussing the y direction, but I am going to put the x's here to remind ourselves that we're talking about the x component of the initial momentum and the x component of the final momentum. It's important to organize your calculations when you're doing these problems, because as you will see, there's a lot of variables and parameters to handle, and if your calculations aren't organized more or less in the manner that I've shown here, you might end up making careless mistakes or getting lost in your own algebra. In this first line, I'm talking about the initial momentum of the system. The system consists of two pieces, so object 1 and object 2. So I'm going to calculate the momentum of object 1 and add it to the momentum of object 2. I'll do that initially, that is before the collision. I'll do the same thing finally, that is after the collision. For each object, the momentum is simply mass times velocity. So I have mass of 1 times initial of 1 plus mass of 2 times initial of 2. That all gives me the initial momentum of the system in the x direction, and I will do a similar thing for the final momentum. I know masses 4 and 1, so I'll plug those in. I know what the initial velocities are. The initial velocity in the x direction of object 1 was 3. Notice the initial velocity for object 2 is -7. The minus reflects the fact that the second object was initially, before the collision, moving in the negative x direction. After the collision, the velocity of object 1 is given to me. We're told that it rebounds with a speed of 0.5. Rebounding or bouncing off implies that it has changed its direction. It's moving with a speed of 0.5 in the negative x direction. For object 2, we know its mass, but we do not know its final velocity in the x direction. That's the variable that we wish to solve for. As you can see, now you have a relatively simple algebraic equation. You can plug all that into your calculator and solve for v2fx. And we find that after the collision, that is finally, object 2 will be moving in the x direction with a speed of 7. A little more specifically, it will be moving in the positive x direction with a speed of 7 meters per second. This is the typical way of organizing your conservation of momentum calculations. I should mention that there is another way of organizing your calculations. No matter what you do, you should learn to organize your calculations because it's easy to get lost in the algebra when you're doing momentum problems. But how you organize it depends on you. Some people prefer organizing their calculations in the form of a table, and so this table at the bottom shows you how you can organize your calculations. We are talking about the X momentum. You could make a similar table for the Y momentum, although for this particular problem, there really isn't much happening in the Y direction. Notice my table has two columns, the initial column and the final column, so before the collision and after the collision. And then I have rows for what's happening to object 1, what's happening to object 2, and then the total of the system, so that would be object 1 and object 2. I've calculated the initial momentum of object 1, so mass times velocity for object 1. I've calculated the initial momentum of object 2, so its mass times its velocity, and then I've added those together to find that the initial momentum of the system, total, is simply 5. That corresponds to this 5 over here. After the collision, I can calculate the final momentum of object 1 because its mass and final velocity are known. That's minus 2. However, for object 2, I know its mass, but I do not know its velocity, so I'll just write it as 1 times v2fx. When I add those together, I get minus 2 plus v2fx. The principle of momentum conservation says that the initial total momentum must equal to the final total momentum. So now I set these equal to each other, and with a line or two of algebra, once again, I can find that v2fx is 7. Doesn't really matter which method you use to organize your calculations. The important piece of all this is to organize your calculations and understand intuitively that what we're doing here is equating two momenta, before the collision and after the collision. Part A of the problem asked us to calculate the final velocities, which we've already done. Part B asked us to figure out what happens to the kinetic energy of the system. Is it conserved? Does it change? Does it go down? Does it go up? It turns out kinetic energy is not always conserved. Under the right circumstances, energy can be conserved, but of course that includes both kinetic energy and potential energy. Here we're specifically talking about kinetic energy, and if we want to know whether the kinetic energy is conserved in this particular collision, we have to simply calculate the kinetic energy of the system. Here I've organized my calculations in the form of a table. Notice I'm now talking about kinetic energy, not momentum. I have two columns again, one for the initial kinetic energy and one for the final kinetic energy. I've calculated the initial kinetic energy of object 1, initial kinetic energy of object 2, and then I've added them together. Remember, kinetic energy is calculated as 1/2 mv squared. So we have 1/2 mass of object 1, initial velocity of object 1 squared, and then similarly for object 2. I've done that initially, and then I've done a similar calculation for the final situation after the collision. I have used the final velocity of object 2, which we calculated in part A of this problem. Putting all this together, we find that the initial kinetic energy of the system is 42.5 joules, whereas the final kinetic energy of the system is only 25 joules. Clearly, kinetic energy is not conserved in this particular collision. You might be wondering, well, where did the energy go? Clearly, before the collision, as these two objects were headed towards each other, they had a lot of kinetic energy, well, 42.5 joules. And then afterwards, as they're moving away from each other after they have collided, they have less kinetic energy. Something must have happened to the missing kinetic energy, and it's not really clear. The problem doesn't give us enough context to answer this question, but in general, when it comes to collisions, kinetic energy gets converted to other forms of energy. If you're talking about the collision of two cars, there might be a loud bang. That bang carries acoustic energy. That sound carries some energy, and that comes from the kinetic energy of the two automobiles. In that same collision, things might break, things might get bent, and that takes a certain amount of energy. It requires work to bend or deform objects. So the fragmentation and deformation of the bumper and other car components also takes some of the kinetic energy away. There might be heat that is generated. We sometimes refer to that as thermal energy. So the kinetic energy can be converted to thermal energy as well. In general, in many of the collisions that we'll consider in this class, you'll see that kinetic energy is lost to these other forms of energy. Doesn't always happen, but it will happen in at least some of the examples that we'll consider. When two isolated bodies collide, momentum is conserved. More precisely, if the sum of the external forces is equal to 0, then we can say P initial is equal to P final. So this is the precise statement of the principle of momentum conservation. So we know what happens to momentum when two isolated bodies collide, but what happens to kinetic energy? Is kinetic energy always conserved in the collision of two isolated bodies? And the answer is no, not always. The practice problem that we just finished doing gave us an explicit example of that. Sometimes kinetic energy is conserved, sometimes it's not. On this basis, we divide all collisions into two categories. Elastic collisions are those collisions where we can say K final is equal to K initial. So if you're told a collision is elastic, then you know kinetic energy is conserved. On the other hand, if kinetic energy is not conserved, so if K final is not equal to K initial, then we have an inelastic collision. In elastic collisions, the kinetic energy remains as kinetic energy, but in inelastic collisions, the kinetic energy is transformed to other forms of energy. Generally speaking, microscopic collisions, like collisions between atoms and molecules on the very small scale, tend to be elastic collisions. When two atoms collide, they don't really make a sound, so the kinetic energy is not converted to other forms of energy. On the other hand, large-scale macroscopic collisions in the everyday world around us, the collisions we can see with our eyes, tend to be inelastic. When two cars collide, they do make a loud sound. A lot of the kinetic energy is converted to acoustic energy or thermal energy or other types of energy. When you're doing collision problems, if you're told the two bodies are isolated, you can immediately start using conservation of momentum, but you cannot immediately start using conservation of kinetic energy unless you're told explicitly or that there's some hints that the collision is elastic. One last bit of terminology that you need to be familiar with is the idea of a perfectly inelastic collision. Perfectly inelastic collisions are inelastic, so the kinetic energy is not conserved. And what makes them perfectly is the fact that the maximum amount of kinetic energy is lost. This happens when the two objects stick together. So from our discussion so far, it is not at all obvious that these are the collisions in which the maximum amount of kinetic energy is lost. But for the time being, you have to be satisfied with the notion that in a perfectly inelastic collision, we can say that V1 final is equal to V2 final. This is precisely what we mean when we say that the two objects stick together. What we mean is that they're basically moving with exactly the same velocity, same speed, and same direction after the collision. Let's end this lecture with a practice problem. Two isolated particles with masses 4 kilograms and 1 kilogram collide with initial speeds of 3 meters per second and 0 meters per second. The collision is elastic. what is the velocity, speed, and direction of each particle after the collision. So we're given a great deal of information about this collision. We have the typical collision situation, two masses, the masses are known, the initial velocities are known. Notice that one of the objects is initially at rest because its initial velocity is 0 meters per second. Notice we're told that the particles are isolated. The fact that they're isolated immediately tells us that we can say P initial is equal to P final. So that phrase or that word by itself immediately gives us at least one equation for solving this problem. Of course, we need to be careful. We need to distinguish between initial and final. We need to distinguish between x direction and y direction. We need to distinguish between particle 1 and particle 2. So there's a lot of subtleties there that we need to pay attention to. But the fact that the two particles are isolated immediately tells us that we have conservation of momentum. Notice a little later, we're told that the collision is elastic, and the fact that it's elastic tells us we can write down another equation. K initial is equal to K final. So the initial kinetic energy of the system is equal to the final kinetic energy of the system. Of course, the system consists of two particles. So when we talk about K initial, what we're really talking about is K initial of particle 1 plus K initial of particle 2. So we'll fill in all of these details in just a minute, but note that the goal is to find the final velocities. This practice problem is a rather difficult one because neither of the final velocities are known. We need to find the final velocity of both object 1 and object 2. So to solve this problem, I have first summarized all of the relevant parameters at the top. I know what the masses are for the two particles, and I know the initial speeds of the two particles. The goal is to find the final speeds or the final velocities. To begin with, I'll use conservation of momentum. Conservation of momentum states that the initial momentum is equal to the final momentum. I have to remember that my system consists of two particles or two objects, and so I need to calculate the momentum of one, momentum of two, and add those together. I'll have to do that initially, and I'll have to do that finally as well, and then set those equal to each other. I can calculate the initial momentum of each particle easily. When I add those together, I find that the initial momentum of the system is 12. The final momentum of the system is 4 v1fx plus v2fx. I don't know what these final velocities are, so I'll just leave them as variables for the time being. Notice I have one equation with two unknowns. I cannot solve for two unknowns with only one equation. We need a second equation to solve for both of those unknowns. For now, all I can do is rearrange this equation and basically express V2 in terms of V1. I now turn to my second equation. My second equation comes from the conservation of kinetic energy. I know kinetic energy is conserved because the problem explicitly states that the collision is elastic. Kinetic energy is 1/2 mv squared. I'll have to calculate 1/2 mv squared for particle 1 and particle 2 and add those together to find the initial kinetic energy of the system, and I'll have to do that finally as well. At this point, I can probably make my life a little bit easier if I immediately cross out all of the 1/2s that I see everywhere. And then I can plug in the masses and the velocities, and I find that on the left side of this equation, I'll get 36. And on the right side, I'll get 4 v1f squared plus v2f squared. v1f is the speed of particle 1. Note that when you're calculating kinetic energy, the v that you put into that equation, 1/2 mv squared, is the speed of the particle. Technically, the speed of the particle is different from the x component of the velocity of the particle. We denote speed using v1f, but we denote the x component using v1f sub x. The difference is that speed is always positive, but the x component can be positive or negative. However, in this context, that distinction is unimportant because we're going to be squaring this quantity. So whether it's positive or negative, the negative sign is going to go away. We're going to end up with a positive number. The important point here is that I have the speed of particle 1, and I'm now going to replace it with the x component of particle 1. So I've rewritten exactly the same equation here, but I've replaced the speed with the x components, and I'm not worried about the fact that they might be negative since I'm going to be squaring these quantities. Now notice again, I have one equation with two unknowns. I cannot solve this equation by itself. However, I do have this earlier equation that we derived. So we're going to substitute the first equation into the second equation. So at this point, what I've done is I've taken this quantity here for V2, and I've simply replaced it or substituted in this quantity here. So now I have a rather messy, complicated equation. I can square everything and simplify it, and I'll get this equation over here. Notice this equation has only V1 in it, V2 has been eliminated. It's a quadratic equation, and I should be able to solve this quadratic equation using the quadratic formula. The quadratic formula always gives you two answers. Often you can eliminate one of them because it turns out to be negative or something nonsensical. In this case, both of the answers are going to be positive. So try the quadratic formula on this equation here and solve for V1f in the x direction, and you'll find that the two answers you get are 3 and 1.8. You'll have to take your V1f and plug it into this equation here for V2f to find the final velocity of particle 2, and when you plug in 3 into this equation, you'll get 0 for V2, but if you plug in 1.8 into this equation, you'll get 4.8 for V2. So now the question is, what's the right answer? Are the final velocities 3 and 0 for the two particles, or are the final velocities 1.8 and 4.8? If you think about this a little bit, you'll see that the correct answer must be 1.8 and 4.8. Why? Well, because 3 and 0 are no different than the initial velocities. The two particles started with initial velocities of 3 and 0. Following the collision, their velocities must change. The only way their velocities could remain unchanged is if the collision did not happen, or if the two particles simply missed each other. For example, you can imagine one particle essentially missing the other particle and passing by it. In that situation, we don't really have a collision, we just have constant velocity motion, which is not at all interesting to us. So the very fact that we know a collision must have happened tells us that the correct answer must be 1.8 and 4.8. And that's the end of this lecture. Thank you for your attention.